Okay, so I'm going to talk about the continuum surveys that will be going ahead over the next few years in the radio wavelengths, mainly with the SK precursor telescopes, LOFAR and MEERKAT and APATITH. I'll leave ASKAP to Andrew Hopkins, who's speaking next. So this is really on behalf of a large number of people all involved in these many surveys. So the first slide here actually shows you what we're used to getting in radio continuum surveys, and that's the powerful AGN type thing. It's for many years been considered sort of a niche area for AGN research, from the extragalactic perspective anyway. But what I'm going to talk about is where we're heading now with these new facilities and new technology allowing us to probe much deeper and much wider area. I've left EVLA off here because its niche area is very much in terms of small area, deeper surveys, whereas the various ones I'm going to discuss are more geared towards larger areas. So why larger area? Well, this applies to all wavelengths we're hearing about. You want to cover as much of the high redshift universe as you can, have a volume-limited survey similar to Sloan at low redshift, and you want to sample all environments, overcome cosmic variance, sample variance, and also study rare objects, which you can only get by studying large areas. And also, for many cosmological measurements, as Bob Nichols said earlier, you want to push that large area to probe very large scales, looking for VAO signals and departures from GR, etc. So, okay, so this is sort of one example of where we are at the moment with, this is a 1 square degree VLA survey over the VVDS field in the XM large scale structure region. And the green contours are the radio continuum. And this goes down to about an RMS of about 20 microjanskits at 1.4 gigahertz. And this is overlaid on data from the VISTA survey, which Steve Warren may talk about later. And you're at around 1,000 objects per square degree in this sort of survey. Over the next few years, with the SK precursors, we'll be pushing 10 to 100 times deeper than this. And that translates to 10 to 100 times more sources. So you can see a field such as this will be absolutely packed with radio continuum sources. And it really is taking us into the regime where the radio continuum surveys will start pushing down with enough sensitivity down to the traditional regimes of optical astronomy, picking out star-forming galaxies at high redshift. So what are the main goals of these large-scale continuum surveys? Well, like I said, rare objects. Some of these are the very highest redshift radio sources. Finding these is actually very good in itself for many science reasons. Mainly, you want to figure out what the space density of these objects and AGN and supermassive black holes are at a high redshift. But it also gives you the opportunity to do an H1 21 centimeter study to actually study the 21 centimeter forest in the epoch of ionization, very much like we use the Lyman alpha forest at low redshift now. Like I said, we'll start picking out star-formed galaxies at high redshift. Also, at such deep levels that the traditional radio quiet AGN, which we generally don't pick up in radio surveys, will be very abundant in these continuum surveys. And again, the traditional radio loud AGN and the sort of traditional realms of radio astronomy as well, but also large cosmological studies, which I'll mention later. So the first of these to come online will be LOFAR. LOFAR is now working to a certain extent. And LOFAR is operating at very low radio frequencies at depths and resolutions that have never really been probed before at these frequencies, nowhere near, actually. And it will also have high angular resolution. So in the general survey, you'll be looking at arc-second resolution over large areas of sky. In the deeper surveys where international baselines come in, you'll be into sub-arc-second resolution at 200 megahertz and below. There are other science aims of LOFAR rather than large continuum surveys. You have nanosecond time resolution in terms of cosmic rays. You'll also be looking for rare transient objects, GRBs and flare stars and what have you, unknown sources. And also the epoch of ionization, which is probably what it's most well known for. Well, I'm not actually going to talk about that. So this is an image from June 2010 of the core of the LOFAR array. These tiles here are the high band, so LOFAR split into a low band and a high band, the middle of which is the FM radio band, which in Europe is obviously quite well packed. And these are the high band operating between 120 and 240 megahertz. The low band, which you can just about see, is these things here, and they're just sort of dipoles in the ground, operating between 10 and 80 megahertz. So LOFAR is now distributed a lot across Europe. It's not just a Dutch telescope. It's actually, there's stations in the UK at Chilbolton, there's stations in France at Nancy, and a number of stations in Germany, and proposed one in Sweden that's just being put together right now. And the combination of all these allow us to get that high resolution and increased sensitivity. So here's an example just to prove they are real. We haven't just made them up over the other side of the Atlantic. They do exist, and they are actually taking data. And I think all the ones in here are actually connected to the Blue Gene supercomputer in Groningen, which is processing all the data. And just to give you an idea, the data rate from here is sort of a terabit per second, coming from station beamforming through to the LOFAR station. So we are actually in the regime of handling massive amounts of data across Europe. So going on to LOFAR surveys, there's an executive team who try to make decisions on survey strategy and what have you. This is led by Hugh Rutgering, and George Miley is also involved. Didn't know George was in the audience, so I had to put Hugh first, otherwise he'd report back and say, Matt's just taken the whole LOFAR survey. There's a technical team led by Neil Jackson from Jodrell Bank, and it's a large number of people involved, mainly lots of people not doing an awful lot at the moment, generally because it's very specialized radio astronomy work, but most of these people are actually in the survey because they actually bring unique expertise, either from a multi-wavelength perspective or through a radio astronomy perspective, and also different science areas. And these are all appointed by various national consortia in various ways. So what is LOFAR surveys going to do? Well, this is the current survey design, and there's basically an all-hemisphere survey at all frequencies, down to millijansky levels. So this is sort of in the regime of a factor of 10 deeper or more than MVSS does right now. There's also tiered surveys, the usual wedding cake. There's a deeper tier covering a smaller area, which is a few hundred square degrees, depending on, or up to 1,000 square degrees, depending on what frequency you choose. Obviously, your field of view gets bigger as you go to a lower frequency. And there'll be an ultra-deep field, and unlike optical and near-infrared ultra-deep fields, which are usually sort of square degree or a couple of square degrees on the sky, the LOFAR ultra-deep field is actually about 100 square degrees, just because of the size of the beam, which is about 3 square degrees in the high band. So there's a number of science cases, and these are split up and led by various people from all the countries involved in LOFAR. So there is data from LOFAR. These are the so-called A team, the brightest radio sources in the sky, observe at LOFAR at various frequencies from 130 megahertz to 20 megahertz, 142 megahertz. I think there's a low band one in here somewhere. But this gives you an idea that LOFAR is actually producing data, and we are correlating it, and we are getting maps out. This is an image of 3C196, a very zoomed-in image of 3C196 using the Dutch core stations. And just to prove that we can also correlate this very low-frequency radio data on international baselines, we have a zoomed-in version at HST resolution at 150 megahertz. This is courtesy of Olaf Wucknitz in Germany, who actually produced this. And you see the 2-point sources that make up the 3C196. So this is by no way automated yet, but it is showing that we are actually correlating this data, and it is going to the depth we want it to, and it actually is working at the resolutions we want it to. And just to compare with a 400 megahertz map from Merlin, which is very well known for its high resolution work, and combining 5 Dutch stations with 3 German stations, you have, again, 3C196 zoomed in at 50 megahertz with the colours, actually the LOFAR data, and the contours, the original Merlin map. So this is now working. I hope I convinced you of that. And over the next year or so, we'll start, hopefully, undertaking the large-scale surveys once we have the imaging pipeline fully operational. So that leads me on. So that's the low-frequency end. I'll come on to the science once I've been through introducing these. This was mentioned in the last talk, and this is APATIF on the Westerbork synthesis array. So this is one of those new focal plane arrays. You'll probably hear a lot more about this in Andrew's talk, which is similar technology that's going on ASKAP. And to open up the field of view from existing radio dishes with basically a CCD, amounts to a CCD camera on a radio telescope. And Aperitif is going to be put on Westerbork, and it increases the survey speed by a factor of 30 over the original Westerbork telescope. Basically, you get an 8 square degree field of view. So we've heard it will also do an H1 survey over a large chunk of the northern hemisphere. Piggybacking on that, it'll also be doing a large continuum survey called WODAN, also led by Hugo Rüttgering and a number of other people. And this is the aim is to go to 10 microjanskis RMS over the whole northern sky, north of a declination of 30. So this hopefully will start in around 2013. And once it starts, the survey speed is so immense, you'll get very deep maps of large chunks of the sky very quickly. This is my one slide on ASKAP, because Andrew is going to cover this. This is the ASKAP version of the continuum survey being done on the SK precursors. And again, it's covering large swathes of the sky, a lot better than MDSS has done, and with a lot greater depth and resolution. And again, survey starts around 2013, depending on how quickly they get it all set up and working. And the last one of these is, because I can't actually go through the SK precursors without mentioning them all for political reasons, particularly as I'm jointly in South Africa. I can't be biased. So this is a South African deep continuum survey called MIGHTY. So Meerkat's niche is smaller areas but a lot deeper. It has a higher collecting area, better resolution, but doesn't have the field of view of something like ASKAP and Aperitif. So these together are very complementary. We cover the whole sky, but we also, with Meerkat and also EVLA to a greater extent, we'll have the sensitivity to push up very deep levels over smaller areas of sky and actually build up that wedding cake survey strategy that you see in multi-wavelength astronomy, and basically volume, the same volume at high redshift that we do at low redshift. So MIGHTY is doing this sort of survey. The tier 1 is actually uncertain, but these 2 tiers here are definitely going ahead. And this will give us around 30 to 40 square degrees down to microjansky RMS levels, so factors of 10 better than what ASKAP is doing and what LOFAR is doing. And in the very deepest tiers, we're really going to try and push down to where no one's ever gone before, the 10th of microjansky level over square degree patches of sky. So how does all this fits together? Well, this is sort of where we are now in terms of this effective flux limit against area. These are all done at various frequencies. So when I say effective 1.4 flux limit, it's usually just taking the standard spectral index to correct that. And this is where we lie. We have deep, narrow surveys, and we have large, shallow surveys. So over the next few years, this is where the LOFAR, Meerkat, and ASKAP surveys fit in. LOFAR and ENU are very complementary in terms of their depth they're going to, even though they're operating at different frequencies. Likewise, the wide field Meerkat survey would have been very complementary to LOFAR, but going down to here is where you see LOFAR, the deep LOFAR, ultra deep LOFAR field, and the Meerkat survey and the very deep Meerkat survey basically all start filling in this area. And eventually, with SKA, we move up to filling this bit up here. So what does that mean in terms of the science? Well, I said we'll be moving away from the traditional realms of radio astronomy where it's generally AGN and rare object science when it comes to the wide area surveys. Well, these are simulations from the work of myself and Richard Willman for the SKA to predict the number density of objects and what kind of objects they'd be as a function of redshift. This is for LOFAR shallow survey, and this is for a LOFAR deep survey. And what you see is the solid line here is actually star-forming galaxies. So almost all redshifts out to redshift 2 to 3, you'll be dominated by star-forming or star-bursting galaxies. You will not be dominated by the AGN. And this is sort of Milky Way type objects out to redshift 1 and 2, depending on which survey you're talking about. And down here are various radio quiet quasars, the next most abundant population, and then you get sort of FR1 type radio galaxies and FR2 radio galaxies that take up a very small fraction of the whole population. So this is where we're going. So we are entering this whole new field of research in terms of radio. So wide field, detecting star-forming galaxies up to redshift 2 and 3. That's actually for, actually, I think, yes, this is per square degree. So there's a few thousand objects per square degree, depending on the which survey and which tier you're talking about. So what does this mean in terms of science? Well, I've taken what has been done with the radio surveys before, basically looking at the AGN luminosity function, the radio allowed AGN luminosity function, and seeing what constraints we got on it. And this is from the Meerkat tier 1, 2, and 3 combination of these colors. And you can also add EMU into there. And these are basically the Poisson uncertainties on the luminosity function of basically the accretion rate density over the history of the universe from redshift 0.5 to redshift 2. And then even at redshift 5, the combination of these allows us to pin down the total AGN output at radio wavelengths across the whole of the universe. And this includes radio quiet AGN. So, well, I said star-forming galaxies is where it's going to be. So if you do the same sort of plot, this is analogous to sort of the Maddow-Lilly plot, the traditionally optical wavelengths. And you can see that, again, this is basically the luminosity multiplied by the density on this side against the luminosity. So star formation rate equivalent on the x-axis and the star formation rate density on the y-axis as a function of this. And you basically see it, even at redshift 1, 2, 3, 4, 5, we have very tight constraints on the star-forming population. And again, that's if you add in EMU data from ASKAP, you really start pinning down the bright end a lot better because it's wide field capability. So that's not all you can do. As Bob Nickel intimated earlier, going to these wide fields allows you to do a lot of cosmology. And that's also true for the radio surveys. And this is similar to what parameters to what Bob described in the survey. Basically, the evolution of the dark energy equation of state, W0 and WA, and also these departures from general relativity, both your scale and a time-dependent departure. And this is work by Alvise Racanelli, hopefully submitted in the next few weeks. These are the sort of constraints you get. In the largest contour here, basically that's what you get from Planck and supernovae. If you start adding the integrated Sachs-Wolf effect from the all-sky radio surveys, you start narrowing this down a little bit. But then you can start adding in things like large-scale structure and cosmic magnification by cross-correlating these radio surveys, which are actually very good at picking up higher redshift objects. And all the low redshift objects are actually quite bright optically, so you can actually start decoupling a foreground population from a higher redshift population and getting a statistical measure of the magnification due to lensing. And all this feeds into this plot here, and you get a reasonably tight constraint at the dark energy parameters, even with just LOFAR all-sky survey. It actually turns out that these radio surveys, generally because of the lack of accurate redshift information, that we've actually assumed we've got no redshift information of these sorts. We just have redshift distributions which we think are reasonable. And we actually do a lot better on tightening the constraints of departures from general relativity. So for our sort of model of departure, it has departed from GR is here, and GR is over here at 1 and 1. And if you, again, combine all these different surveys, particularly the IS integrated Sachs-Wolf effect, and the constraints you get from large-scale structure, you really start nailing this down. And that's generally because of the redshift distribution of the radio sources peaking at those higher redshifts. And this is just from LOFAR. If you start combining EMU and WODAN, which basically cover the whole sky at 1.4 gigahertz, again, you get slightly better constraints just because of the gain in area. But so that's very encouraging. And over the next few years, I think what will be very powerful is we start combining this. This is assumed no redshift information, essentially, on a particular object, with the combination of things like LSST, DES in the nearer term, and the various VISTA surveys that Steve Warren will actually talk about. We'll be able to do a lot better than these and actually start splitting things like the ISW in terms of a low redshift component, and everything else is at high redshift. So you can start pinning down evolution of these parameters quite well. And likewise, cosmic magnification will require that sort of low redshift population to be separated quite cleanly from a high redshift population. And I think we'll be in a position to do that very quickly. So just to summarize, I've only talked about the continuum surveys, because that was what I was meant to do. And also, I hope brought to your attention that the SKA and its pathfinding isn't just about doing H1, it isn't just about doing pulsars, and it's not just about doing the epoch of reionization. There's a whole wealth of science that links very well with the multi-wavelength surveys that we're hearing about in this conference. All these precursor telescopes are actually very complementary, none of which are actually doing the same type of survey with the same type of instrumentation, apart from probably APATIF and ASKAP, but they're in separate hemispheres, so it actually gives you the power of getting the whole sky to the same level. And together they actually build up these, being able to probe volumes of the universe at all redshifts. But it's absolutely paramount that we actually combine this with multi-wavelength ancillary data. And we do that. We're used to doing that in the radio continuum community. So links to things like LSST and Euclid and W1st, which we've heard about, will be very important. And actually the combination of the radio data, which actually has, like I said before, a different redshift distribution to these optical and near-infrared surveys, actually gives you a lot more information than you get from any one survey on its own. I think I'm right in saying, I think Andrew might actually re-emphasize this, EMU is an open consortium, so is the Meerkat survey. LOFAR isn't so open, basically because there's money involved. But EMU and MITI are, so if anyone's interested in looking into getting involved in these, please come and see myself or Andrew. And the SKA is happening, even if the US haven't signed up yet. A lot of other countries have. So I just want to emphasize that we will be getting higher, on a similar timescale to things like LSST and Euclid and W1st, we'll actually be getting very high resolution. We could be in there and get high resolution radio data, I mean sub-arc second radio continuum data over the whole hemisphere. And what that gets you, stuff we're working on, is how does that compare and complement things like weak lensing surveys that you want to do from space with Euclid and W1st. Because the good thing about radio astronomy is you know your beam pretty well, so you're not got that, especially at high frequency, you haven't got the problem of the seeing really making it difficult to get your weak lensing shapes out. And like I said, and also said in the last talk, this continuum imaging coupled with a billion galaxy redshift survey in H1 gives you different and powerful constraints. And also combine this with things like the EOR and the total power analysis of H1 over large scales, and also probing magnetic fields will all be coming out of these radio surveys. So I'll stop there. Thank you.
I wonder if you can speak about confusion limit when you're going extremely deep in some of those surveys.
Okay, so the question was the confusion limit, the depth of the surveys?
So ASKAP, LOFAR, and APATIF are actually been designed to actually sit above the confusion limit. So ASKAP and LOFAR are sort of, well, talk about ASKAP, which is 10 arcsecond resolution, APATIF, which is around 15 arcsecond resolution. They sit above the traditional confusion limit of 30 beams, 40 beams per source. Meerkat and the LOFAR deep survey is where you do start really pushing into the possibilities of confusion. And that's where the long baselines, so where we're going very deep with LOFAR, we're basically introducing the international baselines to get down to that sub-arc second resolution. Now, Meerkat's, with that very deep survey, is trying to go down to 0.1 microjansky. And the real limitation probably there is you will be confused at some level. It is also an issue, and even if you have sub-arc second resolution at that depth, you may actually just happen to hit the natural confusion level. The finite size of galaxies actually does start confusing you. But we don't think with Meerkat we're at that level yet, and we will still be limited by the beam rather than the actual natural confusion. But it is a concern for the SKA.
So very naive technical question. These antennae, they record the amplitude and phase, right? And you correlate afterwards on disk.
Yeah.
Do you preserve the raw data for reanalysis? Because these confusion things, of course, you can come back to them with auxiliary data.
Yeah, I think there's probably different answers to that for each survey. So LOFAR doesn't. I don't think ASKAP is either. But they're quite shallow, so you hope you'll be able to solve the problems on the fly with those two surveys. Meerkat, the data rates from Meerkat won't be so immense that you can't store the UV data. So you will be able to go back and reanalyze it to get to that increased dynamic range and also increased depth.
Okay, we have one more question.
No, I just wanted to add to what the question Michael asked about confusion. I think the low frequencies in LOFAR, we will certainly be in the confusion limit, but I don't think people, I think, should realize that low frequencies, 50 megahertz and below, is a completely unexplored region of spectrum. And so one is really looking at new things, but it's terribly difficult because of the ionosphere, and it's not clear how deep we will go. We'll go a lot deeper than up to possible.
Okay, so the comment was that you're exploring new parameter space with LOFAR at the lowest frequencies, and it's not clear exactly how deep we'll go due to confusion in ionosphere or other considerations.
Yeah, that's right. And I'd just like to point out that the low frequencies, it is new parameter space, but the high frequencies, where we're doing most of the science I've talked about, there's lots of good science you can do at the low frequencies. Most of the science I've spoken about will be done at the high frequencies.
All right, let's thank the speaker, and we'll move on.